So
We're gonna do simulations now.
no, today's just a lecture day. Yeah. Our next ANSYS activity is next Wednesday.
Simulations, are the days we start our activity?
Yeah.
Okay, should I set lecture dates?
Yeah, everything else is lecture days.
Okay.
Mhm. All right, it's 7 o'clock. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, doing good. Full house today. It's all about the 3 people here in person, but you know, it's late. I know. I'd rather be home too. All right, and so today is another lecture day, and so you know, we are going to do ANSYS activities every other week, and so our next ANSYS activity is going to be a week from now. But until then, you know, we're going to lecture. All right, so the topic for today is we're going to do just a brief review of strength of materials. Okay, and so you know, just kind of the nature of this class, you know, because you know this class is meant to be kind of you know, I think the title of the class is like computer methods and engineering design. You know, because of that, you know, a lot of the class ends up being towards a structural mechanics, you know, structural engineering flavor. And so, you know, we're going to be talking about concepts of like stress and deformation and strain a lot in this course. And so, you know, just as a refresher and, you know, just to make sure we're all kind of on the same page about those concepts, what I thought I'd do today is just kind of review those ideas. Okay. And hopefully after today too, that, you know, I know there were a couple questions after the first activity about, you know, what's equivalent stress, what's principal stress. You know, hopefully after today, then those questions should be answered and, you know, we can kind of use those moving forward. All right. Are there any questions I can answer about the activity or about anything before we get started for today? Okay. All right. So let's go ahead and get started. Okay. And so the topic for today is a strength of materials review. Okay. Right. So strength of materials, you know, if you did your undergraduate in mechanical engineering, you most definitely took a course in this. Okay. And so, if I could sum up strength of materials in one word, it's basically the theory, or it's basically the concepts of how objects and structures mechanically deform as when they're exposed to physical loads. Okay. And so a lot of the ANSYS activities that we're going to do in this class have to do with that exact notion. Okay, so we have some kind of object, we have some kind of structure that we have a CAD file for. Okay, and we're going to expose that geometry to some kind of physical load. And so we're going to expose it to constraints. We're going to expose it to forces, pressures. Okay, and we're going to see how they respond, how they deform. Okay. And so strength of materials is basically the study of how that happens. Okay, and so we know, just intuitively, we know that different materials, they're going to behave differently. They're going to have different strength associated with them. They're going to have different deformation patterns. And so, I wanted to review strength of materials so that, to give a little bit of context about the results that we're getting. Okay. All right. And so to start off with, let's start out with the concept of stress. Of course, stress is the thing that we all feel when we have a deadline coming up and we have not started on said thing. Okay, I felt it today as I was kind of rushing to finish a bunch of things. Okay, but when we're talking about stress in a material or stress in a structure, it means something different. Okay, and so its pure definition for stress is basically a force that's distributed over an area. So a lot of times, we may have a structure, we have an arbitrary potato here, okay? And a stress, may be a force that it's being applied to that area. Okay? Right, so the units of force, just like its definition implies, is a force divided by an area. In SI units, the SI unit for force is a Newton. The SI unit for area is meter square. Okay. And so this has units of Pascal. So that is the SI unit for pressure. The SI unit for stress, excuse me. In English units, often we use pound per inch square. English units. And so pound per inch squared, oftentimes you'll see that reported as PSI, where PSI stands for literally pounds per square inch. And you might see variations on this. And so I think for the SI unit, 1 Pascal is very, very small. And so you may see it in terms of kilopascals, kPa, or megapascals, MPa, and so on and so forth. Okay. All right. And so if if you're familiar with like fluid mechanics, then you'll kind of recognize right away that the units for stress are exactly the same as the units for pressure. And so, you may be wondering, why do we have two different names for it? So why do we have pressure and why do we have stress if they have the exact same units? Well, it's true they have the same units. The way that we kind of interpret them is a little bit different. Okay? And so there's just kind of just a little nuance in terms of how you use those terms. Oftentimes when we use the term pressure, oftentimes we refer to, something active. And so something is often exerting a pressure. Right. So if you think back to activity one, remember the load that we applied was a pressure load. And so that's a load that we're exerting onto our plate. Okay. Right. Stress, on the other hand, it's the context that we use stress in is oftentimes reactive. And so oftentimes when you apply some kind of load to an object, stress is formed within that object to keep it in equilibrium. Okay. Right. So even though pressure and stress often have they have the same units, we use them in kind of slightly different contexts. Okay. And so you'll see it, you'll never see, when you're talking about, let's say a structural beam, you'll never hear people say, pressure developed inside the beam. That's not really quite right. So we say that stress develops in the beam. And when you're talking about forces, sometimes you might use the term stress. And so you can say that something's applying like a shear stress onto an object, but most of the times they use pressure in terms of. There's a bit more differences between the two, but I thought I'd kind of highlight just kind of the more common ones, here. Okay. Any questions on this? Okay. All right. So just kind of based on these definitions, you can kind of see what stress is in the context of what we're using. Okay. And so oftentimes we say that stress is going to develop inside a structure in response to kind of physical load. Okay. Okay. And the reason this happens is that, if you think about our ANSYS simulations in particular, the stress develops inside the structures to maintain a sense of equilibrium. Okay, so to maintain basically static equilibrium. So let's do just a very, very simple example. So let's say that we have a rod. And let's say that this rod is pulled in tension. Okay? And so if we look at purely from just the rod as a whole, okay? If we apply the same tensile force on both sides of the rod, then we say this rod is in static equilibrium. because the forces are going to cancel out. Okay. Right, so if we look at the rod as a whole, then we get static equilibrium. That's pretty easy to see. Okay, but one thing that also must be accounted for is the fact that this rod has a non-trivial volume, right? And so it has a length, and so that means that if we split this rod, so let's say that we make a cut along this rod, and we were able to kind of somehow see exactly inside the rod. And we were to take that kind of as a subsystem. And so if we were just to take kind of just the right side of the rod, get kind of the cut plane here. Okay. And so if we look at just that part of the rod there, and we only have the external force on the right, which is the tensile force, right? Right now, the way that I've drawn this, there's no way for this rod to be in equilibrium because the other opposing force is being applied on the other side. Okay, and so what this implies to us, and so what this tells us is that on the inside of this rod, there is an opposing force, an internal force, in other words, that has to oppose that external force. Okay? And that internal force, the way that we often describe it is that it's often described as being distributed on the interior of the structure. Okay, and so oftentimes we talk about this force as an internal stress. Okay. Okay. And so the symbol that we give for stress is often the sigma symbol. Okay. And so this internal stress that must develop has to have a value such that it opposes that external force T. Okay. So the value for this internal stress is T over A, where T right here, this is the external load. And this A, this is the cross-sectional area. So what we say is that, on the internally in the rod, we have an internal stress whose value is T over A. Okay. Because if you take the stress and you multiply it by A, okay, so we do sigma times A. Okay. If we go back to the formula there, then that sigma times A is going to be equal to T. Okay. And so the total amount of force that's being used to oppose the external force has a value of T. And so we have T canceling out with T, and then we have static equilibrium again. Okay. So this formula right here, very simple, but this is kind of the concept of stress in a one-dimensional environment. Questions on this so far? And so, of course, in one dimension, we can come up with a very easy, very simple formula for stress like this. Once you start getting into 2D and 3D and complicated geometries, the equation for stress becomes a lot more complicated. We don't really have straightforward formulas like this that can compute stress in those kind of geometries. But that's the reason we have FEA, right? So the reason we have FEA is that we want to know these stresses because the stresses lead to a lot of other things that we'll talk about, like failure and like strains. Okay, but we don't have a straightforward formula to compute it. And so one of the big benefits of FEA is that we can compute these internal stresses, we can compute these internal forces, without having to do kind of very expensive and very complicated experiments. Okay. All right. So that's kind of the concept of stress. Okay. And so, that's one thing that we're very interested in because it's, even in a one-dimensional case, even if I took my Apple Pencil right here and I kind of pulled on it, that would still be very hard to measure the stress. And so stress analysis, one of the primary kind of benefits of doing FEA. Okay. All right. So let's expand on this idea of stress a bit more. Okay. And so the way I drew it here, the stress looks like it's kind of directly opposing that tension. But stress is actually a multi-directional phenomenon. So you can have stresses that go in multiple directions. And in fact, if you were to kind of mathematically describe stress in a three-dimensional object, stress is not, it's not just a vector quantity. So I think normally, when we think of things occurring in multiple directions, we think of things as a vector quantity, right? So, X, Y, Z components. Stress is actually a lot more complicated because not only do we have the three directions, but we also have two different types of stresses as well, okay? Which we'll talk about soon. And so when we talk about stress, to really fully describe stress in a three-dimensional object, you need what's called a tensor, and a tensor is just a fancy form for a matrix. And so if you were to mathematically kind of write it out, it would look something like this. And so you have stress, okay? You won't see me use this much just because, this is as mathematical as this class will get. But when I'm talking about a matrix or a tensor, I like to put an underline on it. Okay? So I do an arrow on top for a vector and an underline for a matrix. Okay, so for a three-dimensional case, our stress tensor is 3 by 3. We have sigma xx, sigma yy, sigma zz. Okay. Off diagonals, we have tau xy, tau xz, tau yx, tau zx, tau yz, tau z. You can see it's a lot, and there's a lot that we can describe here. Okay, So obviously, if you look at the terms in this matrix, you see X, Y, Z, and so that should be one of the first things that stand out. And so we have different values of stress based on just kind of what direction we're talking about. But you can see here that I've used different symbols as well. And so on the one hand, I have the sigmas, which is the same variable or the same symbol for stress that we used before. But we also have all these taus. Okay. And so there's a reason why I kind of gave these different symbols, because they kind of represent different types of stress. Okay. So let's talk about the two different types of stress that we have. Okay. On the one hand, let's talk about the sigmas first. And so the sigmas, I think, are kind of what people mostly associate with, this idea of stress. We call those normal stresses. Okay, so these are the sigma XX, sigma YY, sigma ZZ. Okay. And so just like its name implies, the normal stresses are ones that act perpendicular to a surface. So visually, they look something like this. And so actually, in fact, the example that we did above had normal stresses. And so if we use the dotted line as kind of our surface that we're looking at the stresses for, then the normal stress would act perpendicular to that normal line. Okay? I know I didn't draw those exactly straight, but those purple lines are perpendicular to the dotted line. All right, the other type of stress that we have are the shear stresses. Okay. And so all the tau symbols are this. Okay, so that we have tau xy, tau xz, tau yz, etc. So the shear stresses are different in that they act parallel to the surface. So let me go ahead and draw the same thing that we have here. And so the shear stresses, instead of acting perpendicular to that dotted line, it's going to be parallel to it instead. All right. Any questions on this so far? All right. So that's the difference between normal and shear stresses. Okay, so that it's mostly dependent on when you cut, basically when you make a cut on a surface, which direction those stresses are acting in. Okay, so you may be wondering, why, if we have normal stresses and shear stresses, I think that might be pretty clear. So why do we have kind of a double lettering here for the directions, right? So the reason we have the double lettering is that, it tells you kind of two informations. And so the first letter tells you which face the stress is acting on. Whereas the second letter, the second coordinate, tells you the direction of the stress itself. Okay. All right, let me show you what I mean. So oftentimes when you're talking about stresses in a structure or even a fluid too. Okay. So if you've taken kind of an advanced, even in undergrad, some covered in undergrad too, of structural mechanics or fluid mechanics, you might be familiar with this figure that I'm about to draw. Okay. I don't like drawing it usually because it ends up being kind of a mess, but it's useful to kind of illustrate kind of what's going on. Okay. All right. So we have a cube here. And so imagine that this cube is kind of an infinitesimally small cube in a structure. Okay? And we're going to use this cube to kind of show you where all the different stress components are acting. Okay? So let me draw my coordinate axes here. And so the x direction we'll say is going to go horizontally from left to right on the page. The y direction is going to go vertically from bottom to up in the page. And the z direction is coming out of the page and going towards you. All right. And so when I talk about, which face the stress acts on, it basically tells you which face on this cube the stress is acting on, right? And so, this face right here, the one that's facing kind of to the right, we call that the X face because if you kind of, if you imagine the face as like a person's face, it's facing in the X direction. Top part of the box, or the top surface of the box, that is the Y face because that faces in the positive Y direction. And the one that's pointing kind of facing right to us, that's the Z face because that's facing in the Z direction. Okay. And then on each of these faces, we have all the components of the stress. Yeah. Oh, really? I see. Well, it's also the second time you're hearing it, so I have the benefit of usually the second time you hear something, it's easier to understand. All right, and so for the X face, we have three components of the stress. And so we have stress in the X direction. Okay. And so that's sigma XX, okay? And so remember, the normal stresses, they act perpendicular to a face. And so, sigma XX is the force on the X face in the X direction. So that's why it's that one. Then we have tau XY. So tau xy is a shear stress that's on the x direction, but it goes in the tau xy is a shear stress that's on the x face that goes in the y direction. Okay, so it's perpendicular to that x face. Okay. And then we have tau xz, which is on the x face, it goes in the z direction. So you can draw the same things. If you draw absolutely everything, it becomes just a mess. But if you're interested, I will draw the rest of them in here. Yeah, it always becomes a mess, and so I don't like drawing it all too much, but it's good to kind of visualize all these different stresses and their different directions. Okay. All right, any questions on this? Okay, so that's stresses. Okay. So stress, is pretty complicated. So when we talk about stresses in a structure, there's kind of a lot to kind of keep in mind here. But at the same time, stress is something that is very interesting. And so if you're doing kind of structural FEAs, stress is kind of what you're aiming to get. And so that's what you want. But as you can excuse me. As you can see here, with the 9 components of stress, it gets to be pretty complicated. And so, when you talk about just stress, you have to ask, are you talking about normal stresses? Are you talking about shear stresses? Which direction are the stresses going to go? And so, usually just kind of by itself, stress, because stress is so complicated, it becomes kind of hard to talk about kind of, when you're talking about, kind of stresses in a structure. So oftentimes, when you talk about stresses, specifically stresses from a finite element simulation, remember, finite element simulations, we're often doing these on very complicated geometries. And so, we're looking at a complicated geometry and this complicated idea of stress, which kind of makes it even more difficult. Okay. And so instead of talking about the individual stress components, oftentimes we like to come up with other measures of stress that are more easy to interpret. All right, and so this is where the concept of like an equivalent stress and a principal stress come into play. Okay? And so equivalent and principal stress, they're computed based on the same kind of stress tensor. And so all the components of stress are there. It's just that we kind of run it through an additional kind of layer of processing just to make it easier to interpret. Okay? And so, of course, there are, there's more interpretations of stress out there. So there's not just equivalent stress and principal stress. It's just that these are kind of the more common ones. So these are the ones that we kind of talk about a lot in this class. Okay? So let's talk about equivalent stress first. And so I think in ANSYS, it calls it the von Mises stress. Still don't know if that's how you actually pronounce his name, because I've heard, equal amounts of people say von Mises, and so, I don't know, maybe we'll dig up, or maybe when I die and go to heaven, I'll ask it, what's the proper way to pronounce his name? Okay. And so the idea about the von Mises stress is that it takes this kind of complicated tensor for stress and turns it into a scalar value. Because oftentimes, it's a lot easier to think about scalar values when you're comparing things. Okay, you can almost think of it as the same way as like taking the magnitude of a vector. Okay. All right, so here's the formula for the von Mises stress. So I'll give it kind of in its purest form. And so the equation that you'll see online for von Mises stress, it's expressed as von Mises stress squared. Okay. So if you wanted to solve for the von Mises stress exactly, you would just take the square root of both sides. But if I took the square root of both sides, would make this tremendously messy. So I'll just leave the square on the left side. Okay, so the formula for this is 1/2. And then we take and we multiply this by quantity, sigma xx minus sigma yy, quantity squared, plus sigma yy minus sigma zz, quantity squared, plus sigma zz minus sigma xx, quantity squared, plus 6 tau xy squared plus tau xe squared plus tau xe.
Six.
Yes, that's 6 right here. So like literally the number 6. All right, so if you look at this formula, you can see that it takes basically all the stress components into consideration. Okay, so of course here you have all the normal stresses. Here you have the shear stresses. You may look at this and say that, hey, we only have half the shear stresses, right? So there should be 6 of them, but I only see 3 in this formula here. The reason for that, that the stress tensor is a symmetric tensor. And so if you kind of swap the letters, then you end up with kind of the same thing. So you have tau xy is equal to tau yx, tau xz is equal to tau zx, and then tau yz is equal to tau zy. These are basically saying the stress tensor symmetric. So that's why you only see, it may seem like there's only half of the shear stresses that are represented in this formula. The reason for that is just that it's symmetric. And so you really only need just one of them, and then you just multiply it by 2, basically. So that's where the 6 kind of comes from. All right. All right, so the von Mises stress, very, very popular. I would say this is the one I kind of see the most because it's a scalar representation, and it's kind of easy to interpret. And so, if you kind of look at this formula here, you can see that you can almost think of it as like the magnitude of stress. And so you take all the components together, you get one number, and that's like just how much stress that it's feeling. Okay. There's been a lot of theory that's kind of built around this idea of von Mises stress as well. And so one thing that we'll use a lot in this class is failure, testing for material failure. Okay. And so you'll see this in activity 2, actually, so a week from today. Okay. And so a lot of times, when you look at kind of the material data sheet, or you look at kind of the, for data regarding a material, so let's say like aluminum, steel, or something like that, okay, they often will report something called a yield strength, or a strength of a material. And so the idea with the yield strength is, so if you look at the units, the units for yield strength are the same as stress. And so it's given in Pascal, megapascal, PSI, things like that. Okay. And so the idea with the yield strength is that if the von Mises stress in the material exceeds this yield strength, then the material will start to break. Okay. So that's known as the kind of the von Mises failure criterion. Okay. Right, it's not always going to be as straightforward as this is. So sometimes if you look up a material, they'll have different yield strengths that they report. And so they may have a compressive yield strength or a tensile yield strength or a shear yield strength. Okay. And so in those cases, you would have to look at the individual kind of normal stresses and shear stresses to determine that. But oftentimes, if you look up a material and it just gives you just one number, it just tells you one yield strength. Oftentimes, you're meant to compare that to the von Mises stress, which is like a scalar representation of that stress. Okay. And so in activity 2, I'll give you kind of a short preview of activity 2. You know, we're basically going to be testing for failure in a bike crank geometry. Okay. And so basically what we're going to do is I'm going to give you a CAD file for a bike crank. So that's kind of the thing that connects to the pedal. Okay. So it's kind of a rod. We're going to apply a load onto that bike crank. We're going to measure the von Mises stress, and we're going to see if that exceeds the yield strength of that material. Okay. Any questions on this? All right, so that's von Mises stress, and so von Mises is, again, just think of it as just a scalar representation of all the stress components. Okay. The other concept of stress that we're going to discuss is principal stresses. So the idea with principal stresses is, the motivation is similar to the von Mises stress, where we want to kind of simplify our interpretation of the stress. It's just that the way that we achieved it for the principal stresses is a little bit different. Okay. All right. So for principal stresses, what people were saying is that this idea of a stress tensor having 9 components of the stress, 6 unique components, is too many components to keep track of. Okay. Instead of transforming the state of stress into a scalar, principal stress, aims to kind of turn the interpretation into a vector instead. Okay. It should be principal. I always confuse those two. Yeah. Thank you. All right. And so the way that principal stresses achieve this is that, it basically wants to eliminate the shear stresses. So how does it do that, right? And so, if you have just a normal, I'm going to do a 2D case here just so it's easier to draw. Okay? And so if you have a two-dimensional square here, right? Normally we have the normal stresses. Isn't? Okay. So this sigma yy. Sigma xx. Sigma yy. Okay. Shear stresses. Tau xy, tau yx, tau xy, tau. Right. And so what some people notice, I think it was a math person, because otherwise it'd be really hard to determine this. What people notice is that when you have a complicated stress situation here, we have both normal and shear stresses, what you can do is you can kind of perform a change of coordinates. Okay? And so instead of looking at this square as kind of like being lined up with the x and y axis, what we can do is we can kind of rotate the square. So instead of the x and y components being like this, okay, you rotate it so that maybe the x and y coordinates are in a different direction. Okay? So we'll call it x prime, y prime. Okay? And then our square is going to be like that as well. Okay? So why would you do this? Why would you rotate your frame of reference? Okay? The idea with the principal stress is that if you rotate your frame of reference in a very specific way, you can get it so that your shear stresses are basically zero, or they are zero, and you change the interpretation of the stress to be only normal stresses. Stress here that by doing this rotation, we're not introducing stress. We're not taking stress away. Like the overall magnitude of the stress is still the same. It's just that we're kind of changing our perspective. We're kind of rotating it a bit to make it align a little bit more conveniently, okay, in terms of computations. Right? And so if you took the von Mises stress, if you computed the von Mises stress of kind of the top configuration and the bottom one, you should get exactly the same thing. Okay? We're just kind of shifting the numbers around and kind of shifting the coordinate axes so that we get it to only this normal state. All right, so this state right here is really nice, because now what we have now is that if you think of a three-dimensional situation, you only have three components of the principal stresses. And so what do we call these three components? We call them literally the maximum principal stress, the minimum principal stress, and the middle principal stress. So most of the time, we're mostly interested in the maximum principal stress. Okay, and that's the one that you computed in activity 1. Because one way that you can interpret the maximum principal stress is that this is kind of the maximum tensile or maximum compressive stress that the material is experiencing at that location. And so once again, this is useful for testing if your material is going to fail, right? Because sometimes when you read up a material data sheet, you're given things like the maximum tensile stress or maximum tensile strength, the maximum compressive strength. Okay, in those cases, it may be useful to compute the maximum principal stress and compare that to the tensile compressive strength. Okay, all right. And so this is kind of another really nice feature in ANSYS. And so this is just trivia, but in order to compute this rotation angle and the directions of the principal stresses, normally that's very computationally intensive. And so you have to solve basically what's called an eigenvalue problem, and you have to solve an eigenvalue problem at each location within your solid, which is very, very difficult. If you've taken an advanced math course and you know a bit about eigenvalues, they are a pain in the ass to compute. So, it is really nice that ANSYS kind of computes these for you. It kind of gives you this information basically for free. All right. Any questions on this? Okay. All right. So that's the concept of stresses. And so, hopefully that gives a little bit more context in terms of, what we're getting out of our ANSYS simulations. Okay? And so the last thing I want to talk about today is, this idea of strain, what strain is, and then how stress and strain are related in a material. Okay. All right. So what is strain? So strain is a measure of the amount of deformation, amount of relative deformation that a structure will undergo. Right, so you have a structure, you expose it to some loads, you expose it to constraints, to some constraints, it deforms. Okay, and so one way that you can kind of describe the deformation is in terms of strain. Okay. All right, so strain is unitless, and so it doesn't have any units. Okay. And the way that you compute it is that it's basically a computation of the change in length or the change in size of an object divided by its original length or its original size. And so in 1D is kind of the most traditional way that it's computed. We have a rod, let's say that we're pulling on it, tension T. Okay. But the original rod may be this length. Okay. And so this distance right here, this is kind of the change in length, and so we'll call that delta L. Okay. If the original length of the rod was L, then the strain, which we often give the symbol epsilon, okay, it's just the ratio of the change in length, delta L. So fairly straightforward, so you've probably seen strain a million times here. Okay? But the reason I'm bringing strain up is that, when you compute strain, the amount of strain that you get is directly proportional to the amount of stress that's within the material as well. And so in the simplest of cases, for a linear material, we have a linear relationship between stress and strain. Okay? And so we have this formula. And so sometimes people call it Hooke's law. We have stress is equal to big E times the strain. Okay. And then this big E here, this big E is known as the Young's modulus. So the Young's modulus is an important property of the material. And so we'll talk a lot more about material properties in a couple of weeks. Okay? But basically, the Young's modulus describes how stiff the material is, or how well the material can resist deformations when exposed to load. Okay? So materials with a higher Young's modulus is going to resist deformations better. Okay? So in other words, materials with higher Young's modulus will require a higher amount of load or higher amount of force in order to cause it to deform. Okay. Okay. All right. So for a linear material, we have a linear stress strain curve. So if you were to draw it, it would look something like this. So the x-axis or the horizontal axis, we have the strain. And on the vertical axis, we have the stress, okay? And so for a linear material, we have just a straight line here where the stress and strain are linearly related, where the slope of this line is the Young's modulus. All right, so the following graph, it's only really valid for linear materials. Okay? And so you may ask, what's a linear material? So we're going to be discussing that a lot in this class. But basically, a linear material is one's generally where the kind of the atomic structure of the material is pretty uniform. So most metals can be characterized as linear. And even for most material, as long as the amount of deformation is relatively small, then most materials exhibit fairly linear stress strain behavior. Right. And so, that kind of begs the question of, what happens when you kind of move away from small deformations, okay? And so for most materials, once you kind of deform it to a certain extent, you kind of reach the point where, you start to deform it permanently, okay? And so after the linear region, most materials have a region that kind of looks like this, where the curve kind of flattens out, where this region here is called plastic deformation. This point right here, where it starts to transition, between linear deformation and plastic deformation, this is often called the yield point. So we'll talk about plastic deformation a lot more later in the class, especially when we talk about different material models. But just know that kind of once you kind of reach past that yield point and you start to get into plastic deformation, then the materials actually starts to permanently deform. Okay? Because the idea with linear deformation is that as long as you kind of stay on this linear curve right here, okay, when you release the load, so let's say that you're kind of at this point right here, okay, when you release the load in the linear deformation region, then the material will go back to its original shape. So you can kind of ride the linear region kind of up and down. Okay? Kind of once you get past that, once you get to plastic deformation, then a lot of that deformation tends to persist. So if you release the load, you may still end up kind of on this part of the strain curve, even with no stress being applied. Okay. And so the last thing I want to go over kind of before we close up today is the relationship for shear deformations as well. Okay. And so what we just kind of discussed here was for mostly for normal stresses. Okay? So normal stress, normal strain. And so for shear stresses, we have kind of a similar relationship. Okay? And this is again for a linear material. Okay. Now, so remember our symbol for the shear stress is tau, or for one of the shear stresses tau. And what we say this is equal to G multiplied by delta. So this tau here is a shear stress. This here is a shear strain. And this G right here kind of plays the same role as E, but instead of being the Young's modulus, this is known as the shear modulus. So just like the Young's modulus, the shear modulus is a measure of stiffness, so it's a measure of strength of the material. But for the shear modulus, this specifically says how well the material resists shearing deformation and shearing stress. All right. So the neat thing about shear modulus is that if you have a purely linear material, you can actually compute this based on the Young's modulus. So the Young's modulus and shear modulus, they're not completely independent. So they are related. And so the formula for that is that G is equal to the Young's modulus E divided by 2 times 1 plus mu. Okay. And so big E here is still the same as before, that's the Young's modulus, but the new parameter that we have here, nu, this is something what's known as the Poisson's ratio. So the Poisson's ratio is another important material property. Okay? And so what the Poisson's ratio measures is how much a material is going to deform in directions perpendicular to the load. Right. So the Poisson's ratio is important. It's for on the one hand, it's used to compute the shear modulus, but it's also used for a lot of other quantities as well. Okay? But it kind of seems redundant because if we think about the amount of properties that we have to specify for a material, we usually don't specify the shear modulus for a material. So in most cases, and this is going to be true for this class, when we specify the properties of material, we usually directly specify the Young's modulus, and we directly specify the Poisson's ratio, and then based on those two things, we use those to compute the shear modulus. And one of the nice things about ANSYS is that it does this kind of automatically. Okay? And so on the activity next Wednesday, we're going to be creating our own custom material. And so I'll show you kind of how to make a custom material in ANSYS. And then you'll see, you'll see that, the only things we're going to specify are just the Young's modulus and the Poisson's ratio. And then the entry for the shear modulus will kind of populate automatically based on that, based on those two. Okay. All right. Any final questions before we wrap it up for today? Okay. All right. So that's all I had planned for today. And so that was our review of strength of materials. And so on Monday, when we pick it up again, we're going to, go back into kind of more FEA stuff. And so we're going to start talking about meshing on Monday. Okay. All right. So thank you guys for coming today. Especially because it's a late night. Sure. I'll answer homework questions afterwards, after the class. Yeah. All right. So thank you guys for coming today. I hope you guys enjoy the rest of your evening. I hope you guys enjoy your weekend, and I will see you on Monday.
Thank you, Dr. Tran.
Wednesday, we're going to do the ANSYS activity.
Good night, Dr. Tran.
Yes. Yeah. Monday's a lecture on meshing. Yeah. Monica, did you want me to look at something for your simulation?
It's a quick question for the